Over the middle of the country, the sky has been doing something it usually saves for spring. On the 17th of June 2026, a powerful storm system swept across the Midwest and set off one of the strongest outbreaks of the year. Tornadoes touched down in at least 6 states. Hail fell larger than baseballs. Winds reached near 80 miles an hour. The thing worth a closer look is not a single storm. It is the pattern behind it, a deep pool of cold air and a fast river of wind sitting over the region in a way that belongs to April, not June. If reports like this one are useful to you, you can subscribe and follow along. Over the next 2 hours, this report walks through how forecasters saw it coming, what happened on the ground, why the air kept rebuilding day after day, and what the science can and cannot yet tell us about why this pattern has settled in and stayed. Start with the air itself, miles above the ground. That is where this story begins. High over the Midwest right now sits a large, slow pool of cold air. Forecasters call it an upper low. It formed up near Canada, over the provinces of Manitoba and Ontario, and it is deeper than the calendar would suggest. Around its southern edge runs a fast band of wind. That band is the thing worth watching. This is what people mean when they say something is forming over the Midwest. It is not a single cloud or one storm, it is a setup. The cold pool aloft, the fast wind around it, and the warm, wet air down at the surface have lined up into a shape that makes storms easy to build and hard to stop. Here is why that matters. Storms need a few simple things. They need warm, moist air near the ground that wants to rise. They need cold air above it to keep that rising going. And they need wind that changes speed and direction with height, which lets a storm spin instead of just fizzling. Right now, the Midwest has all three at once, and in unusual measure. The official read from the National Weather Service is plain about it. The pattern looks more like April than June. In spring, the cold air from the north and the warm air from the south still clash hard, and the jet stream rides low across the country. By mid-June, that clash usually eases. The cold air pulls back north. The jet lifts away. This year it did not. The cold pool dug in over Canada, and the jet stayed strong and far south. Think of the jet stream as a track. Storms ride along it the way a train rides a rail. When the track sits over the Midwest and runs fast, one storm system after another can roll down it. That is the heart of the problem. The region is not facing one bad day. It is sitting under a track that keeps delivering. The scale of it is already clear and confirmed. In a single afternoon and evening, tornadoes touched down across at least 6 states. Hail fell larger than baseballs. Wind gusts reached near 80 miles an hour, and in one spot in Iowa they ran higher still. Tens of thousands of homes lost power. None of that is a forecast. It already happened, and the damage is being counted now. What is less certain is why the pattern locked in place and held. The short answer is that forecasters can see the pieces clearly. They can measure the cold pool. They can track the jet. They can tell you, a day or two out, where the storms will likely fire. The harder question is why the whole arrangement parked itself over the same region for weeks and refused to move on. That is the part still under discussion, and this report will return to it with care. For now, hold on to the picture. A cold pool aloft. A fast river of wind around its edge. Warm, wet air feeding in from the south. Put those together over the flat, open ground of the Midwest, and you get a season of storms running well past its usual time. It helps to know that none of this came as a surprise to the people whose job is to watch it. The setup showed up on the forecast tools days in advance. The risk was named, raised, and shared before the first storm ever formed. That early read is its own part of the story, and it is the reason many people had time to plan. The flatland plays a quiet role too. The Midwest has few hills to break up the wind or trip up a storm. Air moves across it freely. When the jet runs strong overhead, the lower winds can run strong as well, and a storm that starts spinning has room to keep spinning for miles. That open ground is part of why this region sees so many of the country's tornadoes in a normal year, and why a loaded pattern hits it so hard. So the question on the title has a real answer, and it is not a mystery dressed up to scare anyone. Something is forming over the Midwest. It is a stubborn spring-like pattern arriving late. The science can describe it well. What it cannot yet fully explain is the staying power. We will build toward that slowly. The next step is to look at how the warning came together, and how forecasters turned a shape in the sky into a clear call days before the storms arrived. The first sign was not a cloud. It was a line of text from a forecast office in Norman, Oklahoma. That office is the Storm Prediction Center, the part of the National Weather Service that watches the whole country for severe storms. Its job is to look ahead, sometimes a week out, and tell people where the risk is climbing. A full day before the worst of it, that office drew a box on the map. Inside the box, centered on the Chicago area and northern Illinois, it placed a moderate risk. On their scale, that is a level 4 out of 5. It is not the top step, but it is close, and they do not reach for it lightly. A moderate risk issued a day ahead means the ingredients are already showing up clearly on the tools they trust. Here is what those tools are. Forecasters run computer models that take in the current state of the air and project it forward. They read weather balloons that climb through the atmosphere and report the wind, the moisture, and the temperature at each level. They study satellite images that show where the cold pool sits and how the jet curves around it. They put all of that together and look for the pattern that has produced trouble before. On this setup, the pattern recognition was easy and grim. A strong jet was set to nose down across the Midwest. Warm, wet air was building underneath it. The wind was changing sharply with height, the kind of change that lets storms rotate. When a forecaster sees that combination lining up over open ground, the call almost writes itself. The reason the early red matters is simple. It buys time. When the risk is named a day out, emergency managers can stage crews. Airlines can plan around the disruption. Schools and event organizers can shift their schedules. And ordinary people, if they hear the message, can think about where they would shelter before the sky ever darkens. A storm that arrives with no warning takes lives that a storm with a day of notice does not. The forecast came with honest edges. That is worth saying. A moderate risk is not a promise that every town inside the box will be hit. It is a statement of odds. It means severe storms are likely somewhere in that area, and that the worst of them could be strong. Forecasters cannot tell you in advance which single street a tornado will cross. They can tell you the whole region is loaded, and that the afternoon and evening are the hours to watch. There were also clear notes of uncertainty written into the outlook. Some of the danger hinged on small things. Whether an early round of storms would clear out in time, whether the sun would break through and heat the ground, whether a boundary left behind by morning rain would sit in just the wrong place. Those are the details that decide whether a loaded setup produces a handful of storms or a long, violent afternoon. Forecasters flag them plainly rather than papering over them. This is a good moment to clear up a common mix-up. A risk level is not a warning. The outlook from Oklahoma is a heads-up, issued hours or a day ahead for a wide area. A warning is something else. It comes from a local office in the moment for a small area when a storm is actually bearing down. The report will come back to that difference later, because knowing which one you're hearing changes what you should do. The outlook did its job here. The box went up the day before. The level was raised. The message went out through phones, broadcasts, and weather radios across the region. By the time the first storms formed, the warning chain was already in motion, and a great many people knew the day carried weight. It is easy to take that for granted. A century ago, none of it existed. A violent storm simply appeared, and a town learned about it when it arrived. The web of satellites, balloons, models, and offices that gave the Midwest a full day of notice is one of the quiet wonders of modern life, and it ran exactly as designed. With the warning in place, the focus shifts to the air over Canada that started it all. To understand why this pattern hit so hard, it helps to look at that deep, out-of-season pool of cold air and why it sat where it did. The deep pool of cold air aloft is the piece that makes meteorologists pause. It sat far enough south and ran deep enough to feel like a calendar mistake. The official discussions kept circling back to one phrase. The pattern, they wrote, looked more typical of April than of June. To see why that stands out, picture how a normal year moves. In early spring, the country is split. Cold air still owns the north. Warm air pushes up from the Gulf of Mexico in the south. The line between them is sharp, and the jet stream, that fast river of high wind, rides low and strong right along the divide. Storms feed on the contrast. April is, for good reason, one of the busiest months for severe weather in the central United States. By the middle of June, the map usually softens. The cold air retreats toward Canada. The warm, moist air spreads north and settles in. The jet stream lifts away to the north as well, often weakening as it goes. The big clash that drives spring storms eases off. The Midwest still gets thunderstorms, plenty of them, but the violent, organised outbreaks tend to taper. This year the softening did not come. The cold pool over Manitoba and Ontario held its ground and stayed deep. The jet kept its strength and kept riding south, right across the northern plains and into the Midwest. The result was a spring-style clash happening in the heart of summer, with all the summer heat and moisture added on top. That last part is what gives the setup its edge. Spring storms are violent in part because of the wind. Summer storms are violent in part because of the fuel. The warm, wet, unstable air of June is high-octane fuel for a thunderstorm. When you keep the spring wind pattern and pour in the summer fuel, you get storms with both the spin to organise and the energy to grow tall and strong. The two seasons borrowed from each other in the worst way. Why did the cold pool linger? This is where honesty matters. Forecasters can describe the blocking pattern that held it in place. The flow aloft locked into a shape that did not want to budge, and systems that would normally sweep the cold pool along instead stalled. They can show you that on a map. What they cannot say with full confidence is why this particular block set up now, why it favoured this region, and how long it will hold. Those are open questions. Some of them tie into longer trends that researchers are still sorting out, and this report will not pretend to settle what the science has not. It helps to picture the cold pool as a slow whirlpool spinning high above the ground. Around its rim, the water moves fast. That fast rim is the jet. As long as the whirlpool stays parked over Canada, its fast rim keeps brushing across the Midwest, and each pass can carry a fresh disturbance south. Move the whirlpool, and the storms move with it. It did not move, and so the storms kept coming back to the same doorstep. The human effect of that is the part you can see on the ground. The same towns kept appearing in the reports week after week. Places hit by storms early in the month found themselves under warnings again days later. That is not bad luck striking twice at random. It is what happens when the pattern overhead refuses to shift and keeps aiming the same loaded gun at the same map. It is worth holding the alarm in check here. An unusual pattern is not by itself a sign of doom. June has seen wild stretches before, and the region has weathered them. What this pattern did was raise the odds, day after day, that any given afternoon could turn severe. Higher odds over many days add up to a lot of storms. They do not guarantee catastrophe on any single one. So the calendar oddity is real, the mechanism is well understood, and the deeper cause of the block is still being studied. That is the honest shape of it. The fast rim of that whirlpool deserves a closer look on its own. The jet stream did more than steer the systems. It reached down and shaped the storms. That is the next piece. High over the Midwest, a band of wind has been running near 80 miles an hour. That is the jet stream, and on this setup it became one of the main characters. It is worth slowing down to understand what it is and what it did, because it explains a great deal about why these storms turned dangerous. Start with the plain version. The jet stream is a narrow river of fast wind that flows from west to east, several miles up, near the height where airliners cruise. It exists because of temperature. Where cold air and warm air meet, the air aloft speeds up along the boundary between them. The sharper the contrast, the faster the river runs. This year, with the deep cold pool still in place, The contrast stayed sharp, and the river stayed fast. On this setup, a core of that wind ran near 80 miles an hour a few miles up, slicing right across the region. That is a strong jet for any time of year. For June, it is striking. The official notes called the wind aloft excessive, which is the kind of word forecasters use when the readings climb past what a season normally offers. Here is how that high wind reaches down and changes a storm. The key word is shear. Shear means the wind changes as you go up. Down near the ground, it might blow gently from the south. A mile up, it blows harder from the southwest. A few miles up, in the jet, it screams from the west at highway speed. That change, from slow and southerly near the surface to fast and westerly above, is what lets a thunderstorm begin to rotate. Picture a stack of moving air layers, each sliding faster and from a slightly different angle than the one below. A rising column of warm air punches up through that stack. The changing winds tug on the column at each level and set it turning, the way you might set a pencil spinning between your palms. A storm that learns to rotate becomes a different animal. It can last for hours, it can hold itself together, and it can concentrate its spin near the ground into a tornado. That is why the jet mattered so much. It did not just push the systems along the track. It supplied the deep, strong change in wind that turned ordinary thunderstorms into rotating ones. The official discussion said the wind profiles were so strongly tilted toward rotation that the storms were likely to stay separate and spinning rather than merging into one plain line. Separate rotating storms are the kind that produce the long-track tornadoes, and that is what the forecast feared. There is a second gift the jet gives, and it is easy to miss. Fast wind aloft helps pull air up from below. As the jet races over a region, it can act like a vacuum at the top of the atmosphere, encouraging the warm surface air to rise faster than it otherwise would. That extra lift helps storms explode upward in a hurry. Strong wind above and strong lift below feed each other, and the storms grow tall and violent quickly. A useful comparison is a chimney. A fire burns hotter when air draws strongly up the flue. The jet acted like a strong draft over the top of the region, and the storms below burned hot, climbing tens of thousands of feet into the sky in a short time. It is fair to ask whether wind that high up can really matter to someone standing on the ground. It can, and this is how. The storm reaches up into the jet, taps its energy and its spin, and brings the consequences back down as tornadoes, damaging gusts and giant hail. The river of wind itself never touches the surface. Its effects do, again and again. None of this is in doubt. The strength of the jet was measured, not guessed. The shear it created was real and large. The link between that kind of wind profile and rotating storms is one of the better understood parts of the science. Where the uncertainty lives is upstream, in why the jet stayed so strong so late. That ties back to the stubborn cold pool, and to questions still open. With the track set, the fuel loaded, and the wind ready to spin the storms, the only thing left was a trigger. The first one came at dawn, over Iowa, as a fast and damaging line of wind. That is where the action on the ground begins. The first damage of the day came before most people were awake. It came as wind, not as a tornado, and it crossed Iowa in the early hours. By the time it weakened, it had snapped trees, peeled roofs, and knocked out power across a wide stretch of the state. A long, fast line of thunderstorms like this one has a name. Forecasters call it a derecho. The word comes from a Spanish term for straight ahead, and it fits, because the main threat is straight-line wind rather than the twisting wind of a tornado. A derecho is a wall of storms that races in one direction for hundreds of miles, pushing a broad blast of wind ahead of it the whole way. To earn the name, the damage has to stretch far, and the gusts have to stay high over that distance. This one qualified. The numbers from Iowa tell the story plainly, and they are confirmed. Forecasters clocked at least 5 separate wind gusts of 75 miles an hour or higher. The strongest reached 94 miles an hour near the town of Marshalltown. To picture that, 94 miles an hour is the wind speed of a strong hurricane. delivered not by a tropical storm but by a summer thunderstorm sweeping across the plains. The effects matched the readings. Near Marshalltown, the wind heavily damaged a machine shed. Elsewhere in the state, gusts peeled metal roofing off buildings and flipped a trailer near the town of Pella. In Mediapolis, a tree came down on a home. At the airport in Cedar Rapids, an instrument measured a gust of 78 miles an hour. These are not dramatic estimates. They are recorded values and reported damage from across the morning's path. The reason a derecho deserves attention is that it can do tornado-level harm over a far wider area. A tornado is violent but narrow. Its worst damage might span a few hundred yards. A derecho is less violent at any single point, but it can flatten trees and lines across a swath, dozens of miles wide and hundreds of miles long. Add up the total, and a single derecho can leave more people without power than a tornado does, simply because it touches so much more ground. Here the morning line carried a second meaning, one that shaped the rest of the day. It was the front edge of the loaded pattern arriving. The jet had nosed in. The wind aloft was strong. The early storms fired along a leading disturbance and raced east. For a few hours they were the headline, but they were not the main event. They were the opening act, and how they exited would decide how bad the afternoon became. This is where a small detail mattered a great deal. Morning storms often do the afternoon a favour by leaving clouds and cool air behind. That can cap the atmosphere, stabilise it, and rob later storms of their fuel. Forecasters watch for it, because a stabilised afternoon is a quieter afternoon. On this day, the favour never came. The morning line moved so fast that it cleared the region by midday. It vacated the stage and left the door wide open behind it. That speed is worth sitting with. A slow morning line might have parked over the region, kept it cloudy, and held the heat down. This one sprinted. It was gone before noon in many areas, and behind it the sky began to clear. Clear sky in June means strong sun. Strong sun on warm, moist ground means rapid heating. The atmosphere, far from being capped, was about to be recharged. So the morning line did two things at once. It caused real damage on its own, the confirmed gusts and the broken roofs and the lost power across Iowa. And it set a trap for later by leaving fast and clearing the way for the sun. Both of those would matter. It also left something physical behind, drawn on the landscape in cool, rain-chilled air. Those leftover boundaries would become the hinges on which the afternoon turned. Where they sat and what crossed them decided whether worse storms would form. The next piece is that recharge. The story of why a battered region did not get a break and instead saw the air rebuild into something more dangerous than the morning is the heart of how this day unfolded. By midday the storms had gone quiet, and that quiet was the most dangerous part of the whole day. It looked like relief. It was the opposite. The atmosphere was not done. It was reloading. Here is what was happening in that lull. The fast morning line had cleared out, taking its clouds with it. The sun came through. It poured down onto ground that was already warm and soaked with moisture from the storms and the humid air streaming up from the south. That sun did to the lower atmosphere what a burner does to a pot of water. It heated it from below. The warm, wet air near the surface grew lighter and more eager to rise. Forecasters have a measure for that eagerness. They call it instability, and they track how much energy is stored in the air ready to power a storm. On this afternoon, the readings climbed fast into a high range. The official discussions put the stored energy at levels that support strong, deep thunderstorms. In plain terms, the air had become a loaded spring. All it needed was a push to release. The push was waiting, drawn across the land by the morning storms. When a line of thunderstorms moves through, the rain cools the air beneath it. That cool air spreads out along the ground and pools where the rain fell heaviest. The edge of that cool pool is called an outflow boundary. It behaves like a small local cold front. On one side sits the cooler, rain-chilled air. On the other sits the hot, unstable air the sun has been building. Those boundaries are where storms love to form. Along the edge, the warm air is forced to rise over the denser cool air, and rising warm air is exactly how a thunderstorm begins. So the morning line, by clearing out fast and leaving these boundaries behind, did not just open the door for the afternoon. It drew lines on the map showing where the afternoon storms would most likely fire. There is a sharper reason those boundaries mattered on this day. A boundary does more than start a storm. It adds spin near the ground. The cool air and the warm air meet along the boundary with a built-in turning motion, low down where it counts. When a new storm forms right on top of that boundary, it can pull that low-level spin straight into itself. The result is a storm far more likely to produce a tornado, and a stronger one. That is the synergy forecasters feared and named in advance. Two things were coming together at the same time and place. The deep, strong wind shear from the jet was set to make storms rotate high up. The outflow boundaries from the morning were set to feed them spin down low. A storm that rotates both high and low is the kind that drops long-lived, intense tornadoes. The setup had quietly arranged for the storms to form exactly where they could do the most. It helps to see the lull for what it really was. Picture an archer drawing a bow. The drawing is slow and quiet. Nothing is flying, but the energy is building with every inch, and the moment of release is coming. The midday calm over the Midwest was the draw. The sun was the arm pulling the string. The afternoon was the release. This is also why the day caught some people off guard despite the warnings. After a rough morning, a calm noon feels like the storm has passed. It is a natural and human read of the sky. On a normal day, it might even be right. On this day, it was wrong, and dangerously so. The worst was not behind. It was being assembled. None of this part is guesswork. The heating was measured. The instability was measured. The boundaries showed up on radar and satellite. Forecasters watched the spring load and said so out loud, hours before the first afternoon storm went up. The mechanism is well understood, and it played out close to the script. By the middle of the afternoon, the spring was fully drawn. The first towering clouds began to bubble up along those boundaries, reaching for the strong wind above. Within an hour, they would become the rotating storms the whole forecast had pointed toward. Those storms, tall and turning and standing apart from one another, are the next part of the story. In the afternoon, the storms that formed did not link arms into a single line. They stood apart, each one its own tall, rotating tower. That separation was the danger. A storm that stands alone and spins has a name, and it is the most serious kind of thunderstorm there is. Forecasters call it a supercell. A supercell is the rarest type of thunderstorm, and the one most likely to turn violent. What sets it apart is rotation. An ordinary thunderstorm is a simple updraft. Warm air rises, cools, rains, and the storm collapses on its own falling rain within an hour or so. A supercell does something an ordinary storm cannot. Its updraft rotates. That spinning updraft, called a mesocyclone, keeps the rising air and the falling rain separate, so the storm does not choke on its own downpour. Freed from that, it can live for hours and travel for many miles. The rotation comes from the shear described earlier, the strong change of wind with height supplied by the jet. On this afternoon, the shear was extreme. So when the towers went up along the outflow boundaries, they did not just grow tall, they began to turn. The official forecast had said the wind profiles were so strongly tilted toward rotation that the storms would likely stay separate rather than merge. That is exactly what happened. A broken line of supercells formed across northern Indiana, central Illinois and into Missouri in the late afternoon, then spread east and southeast through the evening. Why does it matter that they stayed separate? Because separate is more dangerous. When storms merge into one long line, they tend to compete for the same warm air and produce mostly straight-line wind, like the morning derecho. When storms stand apart, each one has its own clear supply of warm, moist fuel flowing in undisturbed. Each can grow to full strength, each can develop its own deep rotation, and each is free to drop a tornado. A field of separate supercells is a field of separate tornado threats. Picture the difference this way. A single long line of storms is like one wide broom sweeping across the floor. A field of supercells is like a dozen drills, each boring down in its own spot, each able to dig deep. The line spreads its energy thin and wide. The supercells concentrate theirs. A mature supercell has a shape that storm spotters learn to read. The rotating updraft can pull the cloud base down into a lowered, often rounded section called a wall cloud. That is the part of the storm to watch, because a tornado, when it comes, usually descends from there. Up top, the storm pushes so hard against the ceiling of the atmosphere that it bulges above the flat anvil cloud in a dome. That dome is a sign of a violent updraft beneath it. These storms showed those features as they matured across the region. The supercells on this day also fed on the giant fuel supply the afternoon had built. With high instability below and strong shear above, they had everything a thunderstorm could want. They climbed tens of thousands of feet. They produced hail the size of baseballs and larger, which we will come to, and several of them, riding along the boundaries that gave them low-level spin, began to drop tornadoes. It is worth noting how well this matched the warning. The Storm Prediction Center had drawn its moderate risk a day ahead and said long-track tornadoes were likely. The local discussions had named the supercell mode specifically and explained why a plain line was unlikely. Then the sky did just that. This is not hindsight. The forecast described the storms before they existed, and the storms obliged. There is also a quieter point here about how much is genuinely understood. The supercell is one of the most studied objects in all of weather science. Researchers know how it forms, why it rotates, how long it can live, and what to look for. That deep knowledge is why a region could be told, a full day in advance, that rotating storms were coming. The mystery in this story is not the storms themselves. It is the pattern that kept producing them. One of those supercells did more than the rest. It held together and tracked across the ground for more than 20 miles, carving a long path through one Illinois county. That single tornado, and the people in its way, come next. One tornado stood out from all the others that evening. It tore through Effingham County in southern Illinois, and it stayed on the ground for more than 20 miles. A path that long marks a tornado that was both strong and stubborn, the kind a loaded pattern is built to produce. A long track is not just a longer version of a short one. It signals something about the storm that made it. A tornado that lasts for 20 miles came from a supercell with a deep, well-organized rotation, fed steadily by the warm air and the strong wind shear around it. Most tornadoes are brief. They touch down, do their damage in a small area, and lift within a mile or two. A tornado that holds together across an entire county had everything working in its favour and almost nothing working against it. The storm that produced it was part of a family. Earlier in the evening, the same line of supercells had carved a swath of large hail and likely tornadoes farther north. The reports trace a path from near the town of Illiopolis, in eastern Sangamon County, southeast through Decatur, through the small town of Arthur, and on through Charleston before the storm weakened. Then, as the evening went on, fresh tornadic supercells fired to the south, and one of them reached Effingham, where the significant damage was reported. The damage in Effingham County is confirmed, and survey teams are working to measure it fully. That measuring takes time, and this report will explain how it is done in a later chapter. For now, the plain facts hold. A strong tornado crossed more than 20 miles of ground. It damaged buildings. It is among the most serious tornadoes of the entire day. It helps to understand what 20 miles on the ground means for the people in the path. A tornado moving with these storms can travel across the land at highway speed. The storms on this evening were clocked moving quickly, some near 60 miles an hour. A tornado embedded in a storm moving that fast does not give a town long. The time between a warning and the arrival can be just minutes. That is why the early outlook and the local warnings mattered so much. Minutes of notice, used well, are the difference between sheltering and being caught in the open. There is a hard truth in a long-track tornado that is worth saying plainly and without drama. The longer a tornado stays down, the more it can find. Over 20 miles it can cross farms, roads, neighbourhoods, and the open country between them. Each mile is a fresh chance to encounter something in its path. That is why these long-track storms draw the most concern from forecasters, and why the moderate risk had named them as the main fear. The official watch in place captured the stakes. Earlier in the evening, a tornado watch covered parts of eastern Missouri and central Illinois. That watch reached nearly 5 million people and included the cities of St. Louis and Springfield, Illinois. A watch like that does not mean every person will see a tornado. It means the whole area is primed for them, and that anyone inside it should be ready to act on a moment's notice. The Effingham tornado came out of that primed environment. It is fair to pause on the calm side of this. A long-track tornado is a serious event, and yet the system around it worked. The risk was raised a day out. The watch went up over the right area. Local warnings fired as the storms rotated. The path, though long, ran in part through open country. The full toll is still being counted, and this report will not guess at numbers the surveys have not confirmed. What can be said is that a strong, long-lived tornado crossed a wide stretch of Illinois, and that the warning chain gave the people in its path the notice the science is able to provide. The Effingham tornado was the longest track, but it was not the only place the storms reached homes. To the east, across the state line in Indiana, another tornado came down on a community and trapped people inside a building. The response there shows what these storms ask of the people who answer them. That is the next part of the story. In the small Indiana town of Steinsville, a tornado came down on a building and collapsed part of its roof, with people inside. That single moment, confirmed by a local official, puts a human face on the whole evening. It is the point where the wind aloft and the spinning storms became a roof falling on a room with people in it. The account comes from Scott McLaughlin, the president of the town board, who spoke to reporters that evening. He described a structure with its roof collapsed and emergency crews working to reach the people trapped inside. That is the kind of report that arrives in real time, while the storms are still moving, before any survey or final count. It is a first-hand account from someone on the ground, and it tells you what the storm did to one place at one moment. Steinsville was not alone. Across the region, tornadoes touched down in at least 6 states through the afternoon and evening. The list is confirmed. Illinois and Indiana took the sharpest of it, but tornadoes were reported in Iowa, Kentucky, Ohio, and Wisconsin as well. Farther north, near the town of Harper's Ferry, Iowa, a large and dangerous tornado warning went out, the kind of wording the National Weather Service reserves for a confirmed sizable tornado on the ground. A survey team was sent to look at the damage there. When a tornado strikes a small town, the response follows a pattern that holds across the country. The first to arrive are usually the people already there. Neighbours, local volunteers, and the town's own small emergency crews reach the damage first, often within minutes, because they do not have far to travel. Their first job is the one underway in Steinsville: find the people who are trapped or hurt and get them out. That search comes before anything else. It is worth describing what that work asks of the responders. They move into a building that has just been hit, where part of the roof is down and more may be unstable. They work fast because someone may be pinned or hurt, and they work carefully because the structure can still give way. They do this often at night, in the rain, with the storms not yet fully past. The people who answer these calls in small towns are frequently volunteers, and they go in anyway. For anyone who finds themselves in a damaged building after a tornado, the standard guidance is simple and calm. If you can do so safely, stay where you are and call out or make noise so rescuers can find you. Avoid moving through a damaged structure if you can wait for help, because floors and walls may not hold. Watch for downed power lines and gas leaks once you are clear. This is the ordinary official advice, and it holds in nearly every case. The damage in places like Steinsville will be measured in the days that follow, not in the moment. Early reports describe what people can see right away: a collapsed roof, a trapped family, trees and lines down. The careful accounting of how strong the tornado was and how far it travelled comes later from the survey teams. This report will hold to the confirmed first-hand reports for now and let the surveys fill in the rest. There is a steadying point to make here. A tornado striking a town is frightening, and the image of a collapsed roof is a hard one, and yet the system around it did much of what it is meant to do. The risk was raised a day ahead. Watches covered the right areas. Local warnings fired as the storms rotated. Many people had minutes of notice and used them. The response in Steinsville began at once, with neighbours and crews working to reach those inside. The harm was real. So was the help. The tornadoes were the sharpest threat, but they were not the only one the storms carried. The same supercells that dropped them were also throwing down ice, some of it larger than a baseball, heavy enough to break glass and dent metal across whole towns. That hail, and how a summer storm builds something so large, comes next. The same storms that spun up tornadoes were also dropping ice the size of baseballs. In 3 Illinois counties, Moultrie, Douglas and Coles, hailstones measured 3 inches across. 3 inches is the width of a baseball, and stones that size, falling from miles up, hit hard enough to shatter windshields, dent metal roofs, and strip the bark from trees. It can seem strange that a warm June day produces ice at all, let alone ice that large. The answer lies in how high and how hard these storms reached. To make a baseball-sized hailstone, a storm needs 2 things working together. It needs to be very tall, climbing into the bitterly cold air miles above the ground where water freezes, and it needs a powerful rising updraft strong enough to hold a heavy stone aloft long enough to grow. The supercells on this day had both, in unusual measure. Here is how the stone itself forms. It starts as a tiny speck of ice high in the storm. The strong updraft, the same rising column that powers the whole storm, catches that speck and carries it up through a zone of supercooled water droplets, water that is below freezing but still liquid. The droplets freeze onto the speck and add a layer. The stone, now heavier, begins to fall, but the updraft is so strong that it catches the stone again and lifts it for another pass. Each trip adds another layer of ice, the way a pearl grows coat by coat. The stronger the updraft, the more trips, and the larger the stone before it finally grows too heavy for even that powerful rising air to hold. That is why hail size is a clue to a storm's strength. A storm dropping 3-inch hail is telling you, in plain terms, that its updraft is ferocious. Forecasters read it that way. Giant hail and violent updrafts go together, and violent updrafts are the same ones capable of strong tornadoes. The hail and the tornadoes on this day came from the same engines. The damage from large hail is its own kind of trouble. It is rarely as deadly as a tornado, but it is far more widespread. A single severe storm can lay down a swath of damaging hail many miles long and a few miles wide. In that swath, the harm is broad and costly. Roofs are battered, cars are dented and their windshields cracked. Crops standing in the fields can be shredded in minutes, which matters across the farm country of the Midwest, where June crops are still young and vulnerable. The dollar cost of a major hail event can run very high, even when no one is hurt. A word on staying safe from hail, because the guidance is simple and official. The main rule is to get inside and stay away from windows. Large hail breaks glass, and flying glass is the most common way people are hurt. If you're driving when giant hail begins, the standard advice is to stop somewhere safe, such as under a sturdy structure if one is near, and wait it out rather than push on through it. Hail like this passes quickly in any one spot, usually within minutes. It is worth keeping the threat in proportion. Hail of 3 inches is large and damaging, and it is also well within the range these strong storms are known to produce. It is not a freak event. It is the expected product of a violent updraft, and forecasters listed large hail among the day's threats from the start. The size is striking. The cause is ordinary for a storm this strong. there is a quiet wonder in it too, worth a calm moment. A stone of solid ice, the size of a baseball, was built layer by layer inside a summer cloud and then fell to the ground in the heat of June. It is a sign of just how much energy these storms held and how high they reached that they could assemble such a thing at all. The hail and the tornadoes drew the most attention, but across the widest area, it was the wind that did the most. The straight-line gusts touched far more ground than any tornado, and they are the threat people most often underrate. That wind is the next piece. Across the whole event, the threat that touched the most ground was not the tornadoes, it was the wind. Straight-line gusts near 80 miles an hour and higher in places swept across far more territory than any single tornado, and they account for a large share of the harm. Yet straight-line wind is the threat people most often wave off, and that is exactly why it deserves a clear look. The standout reading came from Iowa in the morning, a gust of 94 miles an hour near the town of Marshalltown. Through the afternoon and evening, the supercells and the lines they formed pushed out broad swaths of damaging wind, with gusts that reached near 80 miles an hour over a wide region. These are confirmed measurements and reported damage, not estimates. The difference between straight-line wind and a tornado is worth making plain, because it shapes how people respond. A tornado is a narrow spinning column. Its wind twists, and its worst damage is concentrated in a path often only a few hundred yards wide. Straight-line wind is different. It blows in one direction, pushed out ahead of a storm, and it can hit a swath miles wide and many miles long all at once. The wind in a strong straight-line event can match the wind in a weaker tornado. It simply does it over a far larger area. Here is why people underrate it. A tornado is visible and famous. It has a shape you can see and a reputation everyone knows. Straight-line wind has neither. It arrives as a sudden, hard push, often hidden in rain, with no funnel to point at. People who would take shelter from a tornado will sometimes stand at a window to watch a line of storms come in, not realizing that the wind alone can do tornado-like damage. Each year, damaging straight-line winds cause a large share of severe weather harm, more than their quiet reputation would suggest. The damage from this kind of wind follows a familiar pattern, and Iowa showed it in the morning. The wind brings down trees, and the falling trees land on homes, cars, and power lines. It snaps power poles, as it did near a major highway in the town of Macon. It peels metal roofing off buildings, as it did across Iowa. It can flip a trailer, as it did near Pella, or wreck an outbuilding, as it did near Marshalltown. None of these requires a tornado. The straight push of 80 or 90 miles an hour is enough. Power loss is the broadest consequence because the wind attacks the grid directly. Trees fall on lines, poles snap. Across the affected states, more than 82,000 homes and businesses lost power, with Illinois alone reporting more than 23,000 outages at one point. That is the wind signature. A tornado cuts power along a narrow path. A wind event darkens a whole region at once. The safety guidance for damaging wind is the same calm advice that holds for the storms in general, and it is worth stating clearly. When a severe thunderstorm warning is issued, treat the wind as a real threat, not a lesser one. Get inside a sturdy building away from windows. Do not wait outside to watch the line arrive. After the storm, stay well clear of any downed power lines and assume they are live. Most wind injuries come from flying debris, breaking glass and falling trees, and all three are avoidable by being indoors and away from windows when the storm hits. It is worth keeping a steady head about it. 80-mile-an-hour wind is dangerous and capable of real damage, and it is also a known expected product of storms this strong. The grid is built to be repaired. Crews were already staging before the storms arrived because the risk had been named a day ahead. The outages, while wide, are the kind that utilities restore over hours and days, not the kind that lasts. The harm is real, and the recovery is routine. All of this damage, the wind and the hail and the tornadoes, set off a vast response, run through a system of warnings and crews that moved before the first storm and kept moving long after. That system, and the scale of what it managed in a single evening, is the last piece of the first half. A single forecast office, the National Weather Service in Lincoln, Illinois, issued 58 warnings in one day. That number, by itself, captures the scale of what the region's warning system handled. Each warning was a separate alert for a separate threat: a tornado bearing down, a severe storm approaching, a flash flood beginning, sent to a specific area at a specific time. 58 from one office, in one day, is the mark of a relentless afternoon and evening. It helps to understand what a warning is and where it comes from, because it is the sharp end of the whole system. The early outlook from Oklahoma, described earlier, is the wide advance heads up. A warning is the opposite in scope. It is local, immediate and small. It comes from the regional forecast office when a storm is actually bearing down on a defined area, often based on what the radar shows spinning or what a trained spotter reports seeing. A warning means the threat is happening now, here, and that people in its path should take cover at once. On this day, the warnings came in a flood, because the threats came in a flood. The map of warnings issued across the region showed a vast swath stretching from Iowa southeast into the Ohio River Valley. Tornado warnings, severe thunderstorm warnings, and flash flood warnings overlapped and stacked as the storms moved through. The watches that set the stage were broad. One tornado watch alone covered nearly 5 million people across eastern Missouri and central Illinois. Another severe thunderstorm watch took in parts of northeast Iowa, southeast Minnesota, and southwest Wisconsin. The flash flood warnings are worth a note, because the storms brought more than wind and hail. They brought heavy rain. In central Illinois, towns reported water covering highways and standing water in yards. One stretch of a state highway near the town of Bellflower was reported covered in both lanes. 2 inches of rain fell in one town in a short span, with higher amounts measured nearby. Flooding is a quieter threat than a tornado, but it is a leading cause of storm deaths, most often when people drive into water across a road and underestimate its depth and force. The standard advice is the simplest in all of weather safety: turn around, do not drive through water on a road. The wind's main mark on the system was the power grid. Across the affected states, more than 82,000 homes and businesses lost electricity. Illinois carried the heaviest load, with more than 23,000 out at one point. Behind that number is a large coordinated response. Utility crews stage before a forecast event like this one, moving trucks and workers toward the areas expected to be hit so they can begin repairs the moment the storms pass. Because the risk had been named a full day ahead, that staging was already underway when the first lines moved through. This is the part of the story where the early warning chain pays off in full. The outlook went up a day before. The watches covered the right areas. The local warnings fired storm by storm. Emergency managers, utilities, airlines, and ordinary people all had time to act on the information. None of it stops a tornado from crossing a field or wind from snapping a pole. What it does is give people the minutes they need to be somewhere safe when it happens, and it puts the repair crews close by for when it is over. It is worth pausing on how much human effort sits inside those 58 warnings. Each one was a decision, made fast by a forecaster watching radar and weighing what they saw. Issue too few, and a storm catches people unready. Issue too many, and people start to tune them out. The forecasters in Lincoln and the surrounding offices threaded that line through a long and dangerous evening, sending the alerts that sent people to shelter. The storms gradually shifted south and east of the region late in the evening, and the wave of warnings eased with them. The grid will be restored over hours and days. The survey teams will go out to measure what the tornadoes did. The immediate danger passed, as it always does, leaving the counting and the cleanup behind. That counting, and the wider story it belongs to, is where the second half of this report begins. This day was not the first of its kind this month, and to understand why it happened, the next step is to look back at the record it is measured against, and at the long, restless stretch of weather it is part of. To understand how unusual this stretch of weather is, it helps to know the record it is being measured against. That record belongs to June of 2008. It stands as the busiest June ever recorded for one particular kind of severe weather, the damaging wind report. In that single month, the country logged 5,554 reports of severe wind. No June before or since has matched it. It is the high water mark, the year every active June is compared to. A wind report is worth defining, because it is the unit forecasters use to keep score. Each time a storm produces a damaging gust, and someone measures it or sees the damage it caused, that becomes a report. A snapped power pole, a downed tree, a peeled roof, a measured gust above the severe threshold, each can count. Add them across a month and you get a rough but honest tally of how often and how widely the wind has done harm. 2008 piled up more of those than any June in the books. What made that year stand out was not a single storm. It was relentlessness. The pattern stayed active week after week, sending one round of storms after another across the central and eastern parts of the country. The total did not come from one catastrophe. It came from many busy days stacked on top of each other, the same way a long rainy season fills a reservoir not with one downpour, but with steady, repeated rain. That is exactly the shape of the current stretch, which is why the comparison keeps coming up. This June has not produced one storm worse than anything in history. What it has produced is day after day of severe weather, returning to the same broad region, refusing to let up. It is competing with 2008 not on the strength of a single event, but on the sheer count of busy days. Early in the current month, the numbers were already historic for the date. Through the first 16 days, the country had logged more than 2,700 reports of severe wind. That figure is the second highest ever recorded for that span of the calendar. The only June that ran higher through its first 16 days was, fittingly, 2008, which had reached 3,619 by the same point. The current year is chasing the record holder step for step. It is important to keep this in proportion, and the calm read matters here. A record number of wind reports does not mean a record number of disasters. Many of those reports are single-downed trees or brief gusts that hurt no one. The tally measures how active and widespread the weather has been, not how many lives were lost. A historic count of busy storm days is a meteorological milestone, not by itself a humanitarian one. There is also a question of fair comparison that honest accounting has to admit. The way reports are gathered has changed over the years. There are more people now, more weather stations, more cameras, and more ways to log a gust or a fallen limb than there were in past decades. Some of any year's high total reflects better counting, not just busier weather. Forecasters know this, and weigh it when they compare years. It does not erase how active this stretch has been. It does mean the comparison across decades is not perfectly clean. Even with that caution, the standing of this June is clear. It is among the most active starts to the month on record, running close behind the all-time leader. The pattern that produced the outbreak at the centre of this report is the same pattern that drove the count so high. The strong jet, the deep cold pool, the steady supply of warm moist air, all of it kept the storms coming day after day in a way that only a handful of past Junees can match. The year it chases, 2008, sets the bar. Whether this June clears, it depends entirely on what the rest of the month does, and that is not yet written. If the active pattern holds, the total could climb toward the record. If it relaxes, the count will settle where it is, high but short of the mark. Forecasters are watching, and the answer will come in the days ahead. That running tally, and the string of busy days behind it, is worth laying out in order. Before this outbreak, the month had already delivered several rounds of severe weather to the same weary region. Seeing them in sequence shows just how little rest the Midwest has had. That sequence is next. The outbreak at the centre of this report was not the first of the month. It was the latest in a long string, and the same towns kept appearing in the reports. To see the full weight of it, the busy days are worth laying out in order, because the pattern reveals itself only when you watch it repeat. The trouble started early and stayed. By the time the first half of the month had passed, the country had logged more than 2,700 reports of severe wind, the second highest count ever recorded for that span. That total did not come from one event. It came from a series of them, each adding to the pile, each falling on a region that had not yet recovered from the last. One of the sharpest stretches came in the second week. Between the 7th and the 12th, the central and eastern parts of the country saw more than 1,700 storm reports. Inside that window sat an especially busy 3-day run. From the 10th through the 12th, the country recorded 2,392 storm reports across 41 states. That is one of the busiest 3-day spans of the entire season. Alongside it, the National Weather Service issued more than 1,400 watches, warnings, and advisories. The system was working at full stretch for days on end. There was a separate smaller barrage on the 11th, a localised cluster of tornadoes that struck within that same active week. And earlier in the spring, back in April, the country had already seen a high-end, violent tornado in Oklahoma, a sign that the season was charged from early on. The June outbreaks did not come out of a quiet year. They came out of a year that had been active for months. The cruelest part of the pattern was its aim. It kept returning to the same map. The outbreak in the middle of the month struck areas that had been hit hard just a week before. Cities that had cleaned up after one round, places like the corridor from Chicago to St. Louis to Indianapolis, found themselves under watches and warnings again. This was not bad luck repeating by chance. It was the stuck pattern overhead, described earlier, aiming the same loaded setup at the same region time after time. The human cost of that repetition is different from the cost of a single disaster, and worth naming plainly. When storms keep returning to the same place, the strain accumulates. Crews that repaired power lines one week are back out the next. Families that cleared debris do it again. Emergency managers who staffed up for one event barely stand down before staffing up for the next. The total damage rises not in one dramatic jump, but in steady increments, and so does the fatigue of the people who absorb it. It is fair to keep a steady head about the count itself. A historic number of busy days is striking, and it is also, in part, the product of how the country is built now. More people, more sensors, and more reporting mean more reports than a similar pattern would have generated decades ago. The weather has been genuinely active. The record-keeping has also grown more complete. Both things are true, and an honest tally holds them together. What is not in doubt is the lived experience of the month. For the people in the central part of the country, June has been one long sequence of storm days, broken only by short lulls that turned out to be reloads rather than relief. The outbreak in the middle of the month was the most intense single day, with its long-track tornado and its baseball-sized hail. But it sat inside a month that had been hammering the same region for weeks. That sequence, laid out in order, is what makes the title's question more than a tease. Something has been forming over the Midwest, and it has been forming for the better part of a month. The storms are the visible part. The pattern that keeps producing them is the deeper story, and it is the part that has people genuinely asking why. So the next step is to face that question directly. Forecasters understand the mechanism well. The harder question, the one the title points at, is why the whole arrangement locked in and held over the same ground. That is where the honest edges of the science are, and it is worth walking through them with care. That question is next. Here is the question the title asks, put plainly. Why has this kept happening to the same region day after day for the better part of a month? The honest answer comes in two parts. One part is well understood. The other is genuinely open, and pretending otherwise would do the listener no favours. Start with what is understood, because it is most of the picture. The storms themselves are no mystery. Forecasters can see the deep cold pool aloft, measure the strong jet around it, track the warm moist air feeding in from the south, and predict, a day or two out, where the storms will fire. The mechanism that turns that setup into tornadoes and damaging wind is one of the best studied parts of the science. None of the individual outbreaks came as a surprise. Each was forecast before it formed. The open question is not why the storms happened. It is why the pattern that produces them parked itself over one region and refused to move. That comes down to something forecasters call a block. The flow of air high in the atmosphere usually keeps moving, sweeping systems along from west to east. Sometimes it locks into a shape that resists that movement. A ridge of high pressure sets up and acts like a boulder in a stream, forcing the flow to bend around it and holding the pattern in place. When that happens, whatever weather is underneath the bend, storms in one place, heat in another, gets stuck there too. That is what happened here. A blocking pattern held the deep, cold pool over Canada in place and kept the storm track aimed at the same broad region for weeks. Forecasters can describe that block. They can show it on a map. What they cannot say with full confidence is why this particular block set up now, why it favoured this region, and why it held as long as it did. Blocks form and break for reasons that are still not fully predictable beyond a week or so out. That is a real limit, and it is the heart of the title's mystery. There are larger factors that may be tilting the odds, and they are worth mentioning with care. One is the state of the Pacific Ocean. In certain patterns, often called La Niña, the broad flow across North America tends to shift in ways that favour more severe weather across the plains and Midwest. That is a tendency, not a switch. It nudges the odds over a season. It does not dictate any single month. Forecasters watch it, but they do not lean on it to explain one stretch of weather. A second factor is the longer trend in the climate, and here the honest course is to be measured. A warmer atmosphere holds more moisture, and more moisture is more fuel for storms. Researchers are actively studying how a changing climate may be shifting the frequency, the location, and the season of severe weather in the United States. Some patterns are becoming clearer, others remain debated because severe weather is local, brief, and hard to track cleanly over long spans. It would be wrong to pin this 1 month on any single cause, and equally wrong to claim the broader trends have nothing to do with it. The careful statement is that the ingredients have been unusually favourable, that several factors may be raising the odds, and that the science is still working out how much each one contributes. So the title's claim that no one knows why is partly right and partly overstated. No one can yet say with confidence why this exact block formed and held over this exact region at this exact time. That is true, but it is not the case that the storms are inexplicable or that forecasters are baffled. They understand the machinery in fine detail. The open question is narrower and more specific than the title suggests, and it sits at the edge of what current science can predict. That is the calm and honest shape of it. The storms are explained, the pattern is described. The deeper cause of the block, and how much the larger trends are nudging it, is still being worked out. Anyone who tells you they know the full answer is reaching past the evidence. With the why laid out as far as it honestly goes, it helps to return to the basics and look at the simple recipe that every one of these storms followed. 4 plain ingredients working together made all of it possible. Those 4 ingredients are next. Every storm in this long stretch, no matter how violent, was built from the same 4 ingredients. Forecasters look for them the way a cook checks a recipe. When all 4 are present and strong, severe weather becomes likely. When one is missing, the storms fall apart. Laying them out in plain terms makes the whole month easier to understand. The first ingredient is moisture. Warm, humid air is the fuel. A thunderstorm runs on water vapour, the invisible moisture carried in warm air, which releases energy when it rises, cools, and condenses into cloud and rain. The more moisture in the air near the ground, the more fuel the storm has. The main source for the central United States is the Gulf of Mexico, far to the south. When winds carry that humid Gulf air north into the plains and Midwest, they are hauling in fuel. This month that flow ran strong and steady, and the air over the region grew thick with moisture. The second ingredient is instability. This is the air's eagerness to rise. It happens when warm air sits near the ground and colder air sits above it. Warm air is lighter, so it wants to lift, and when there is cold air aloft to keep it rising, it can shoot upward for miles. Forecasters measure how much energy is stored in that arrangement. The afternoon heating described earlier, sun pouring onto warm, moist ground, is what built the instability on the worst day. High instability means a storm, once started, can grow tall and powerful in a hurry. The third ingredient is lift. Fuel and instability are not enough on their own. Something has to give the air its first push upward to get a storm going. That push can come from several places. A cold front can wedge under the warm air and force it up. A boundary left behind by earlier storms, like the outflow boundaries from the morning, can do the same. The fast jet stream overhead can help pull air up from below. On this setup there was lift to spare, from fronts, from boundaries, and from the jet, which is part of why storms kept firing. The fourth ingredient is shear. This is the change in wind with height, the slow southerly breeze near the ground giving way to the screaming westerly jet above. Shear is what separates an ordinary thunderstorm from a violent rotating one. It sets the rising air spinning and lets a storm organize, last for hours, and produce tornadoes. The extreme shear from the strong jet is what made this month's storms rotate, and rotation is what made them dangerous. Here is the key point about the recipe. Severe weather needs all four ingredients at once. Plenty of summer days have moisture and instability but little shear, and they produce ordinary afternoon thunderstorms that rumble and rain and fade. Plenty of spring days have strong shear but not enough warmth and moisture, and the storms stay weak. What made this stretch so dangerous was that all four ingredients were present and strong at the same time, day after day. The moisture poured in from the south. The sun built the instability. Fronts and boundaries supplied the lift. And the unusually strong jet, the out-of-season piece, supplied the shear. It is the combination that matters, and the combination is rare. Think of it like a fire that needs fuel, air, heat, and a spark together. Take away any one and the fire does not catch. This month, all four were stacked over the same region for weeks, and so the storms caught again and again. Knowing the four ingredients also explains why forecasters could see the trouble coming. They do not have to predict a storm directly. They watch for the ingredients to gather. When the models show moisture surging north, instability building, lift arriving, and shear strengthening, all in the same place at the same time, the forecast almost writes itself. That is exactly what happened ahead of the worst day, which is why the moderate risk went up a full day in advance. One of those four ingredients deserves a closer look, because it came from an unusual direction this month. The moisture that fueled these storms traced back to the Gulf, and at the same time, a tropical storm was churning near the Texas coast. The link between the tropics and the Midwest is the next piece. While the Midwest was being hammered, a tropical storm named Arthur was spinning near the coast of Texas. The two events were separate, but they were not unrelated. Both drew on the same vast supply of warm, moist air, and the connection between the Gulf of Mexico and the storms of the Midwest is worth understanding, because it is the thread that ties so much of the country's summer weather together. Start with Arthur itself and the confirmed facts. It strengthened into a tropical storm near Galveston, Texas, with maximum sustained winds reaching 45 miles an hour. The National Hurricane Center extended its tropical storm warning southward along the Texas coast to the town of Sargent. Coastal flooding and strong winds were already becoming a problem along the shore. A tropical storm is the stage below a hurricane, with sustained winds between 39 and 73 miles an hour. Arthur sat in the lower part of that range, more a heavy rain and flood threat than a wind catastrophe. The greater danger from a storm like Arthur is water, not wind. Forecasters placed a high-level threat for excessive rainfall across parts of the southeast for several days running. Rainfall rates of up to 3 inches an hour were possible, and totals could exceed 10 inches in spots. Even as the storm was forecast to weaken and fall apart over Texas, The moisture it had pulled north was expected to keep feeding heavy rain well beyond its centre. That is a common pattern. A tropical system can dissipate as an organised storm, while its leftover moisture goes on to cause flooding far inland. Now the connection to the Midwest, stated carefully so as not to overclaim. Arthur did not cause the Midwest outbreak. The two systems were driven by different forces in different places. What links them is the source of their fuel. The Gulf of Mexico is the great reservoir of warm, moist air for the central and eastern United States. In summer, winds draw that air northward, and it becomes the moisture ingredient for storms across the plains and Midwest. A tropical storm in the Gulf is one sign, among others, of just how warm and moisture-rich that whole region was this month. Think of the Gulf as a warm, wide bathtub feeding humid air into the country. When the bathtub is especially warm and full as it was, there is more moisture available for everything downstream. Some of it spins up into a tropical storm near the coast. Some of it streams 1,000 miles north to fuel supercells in Illinois. The same reservoir supplied both. That is the honest version of the connection. Not that one storm caused the other, but that both fed from the same unusually rich supply. This matters for the larger picture of the month. The persistent flow of Gulf moisture into the Midwest was one of the 4 ingredients that kept the storms coming. As long as that southerly flow stayed strong, the fuel kept arriving day after day. A tropical system parked near the coast can reinforce that flow, strengthening the winds that haul moisture north ahead of it. So while Arthur was not the trigger, its presence was a marker of the moisture-loaded state of the whole region. It is worth keeping the alarm in check here too. A weak tropical storm near Texas is a serious local event, mainly for flooding, and it is also a routine feature of the season. The Gulf produces tropical systems every year. Their main inland danger is rainfall, and the standard guidance for that is the simplest in weather safety. Do not drive into flooded roads. Most deaths in inland flooding come from vehicles entering water that is deeper or faster than it looks. The Gulf connection rounds out the picture of why the Midwest stayed so wet and so primed. The moisture had a clear source, and that source was running rich. Combine it with the out-of-season jet and the stubborn block, and the long siege of storms makes sense from end to end. With the ingredients and the moisture source laid out, it is worth returning to the single most feared product of these storms and explaining step by step how it actually comes to be. A tornado is the part everyone fears most, and it is also the part most often misunderstood. How a tornado is born is next. A tornado is the part of these storms that everyone fears, and also the part most often pictured wrong. It does not drop from the sky as a finished funnel. It is built step by step inside a rotating storm, and understanding the steps takes away some of the mystery without taking away the respect it deserves. Begin with the storm that makes it. As covered earlier, a tornado almost always comes from a supercell, the rare thunderstorm with a rotating updraft. So the first step toward a tornado is a storm that has already learned to spin. That spin, the broad rotation high up in the storm, is called the mesocyclone. It comes from the wind shear, the change in wind with height supplied by the jet. Without that broad rotation in place first, there is no tornado. This is why forecasters watch the shear so closely. It is the seed of everything that follows. The next step is to bring that rotation down toward the ground and tighten it. The broad spin high in the storm is too wide and too high to be a tornado. Something has to concentrate it into a narrow, fast-spinning column near the surface. This is the part the science understands less completely than the rest, and it is honest to say so. Forecasters can tell you a storm is capable of a tornado. They cannot always tell you in advance whether that storm will actually produce one. Two storms can look nearly identical, and one drops a tornado while the other does not. The final step of tornado formation still holds open questions. What is understood is the role of the low levels of the storm. Near the ground, the storm's own rain-cooled air and the warm inflowing air interact in ways that can create and stretch small areas of spin. When the storm's powerful updraft tilts that low-level spin upright and stretches it, the rotation tightens and speeds up. The principle is the same one a figure skater uses. Pull your arms in and you spin faster. As the column of spinning air is stretched and narrowed, it whirls faster and faster until it reaches the ground as a tornado. The boundaries described earlier play directly into this step. An outflow boundary, the edge of cool air left by earlier storms, comes with built-in low-level spin. When a supercell moves over one, it can ingest that ready-made spin and tighten it far more easily. That is why the forecast feared the storms forming right on the morning's boundaries. The boundaries handed the storms exactly the low-level rotation that the hardest step requires. Once the column reaches the ground, it becomes visible in two ways. There is the funnel of cloud, formed as the low pressure inside the spinning column cools the air and condenses moisture into a visible cone. And there is the swirl of dust and debris at the surface, lifted by the wind. Sometimes the debris swirl appears before the funnel fully reaches the ground, which is why a tornado can be on the ground and doing damage before a clear funnel is visible. This is one reason warnings do not wait for a perfect funnel. By the time the picture is clear, the damage may already be underway. The strength of a tornado depends on how tightly that column concentrates the spin and how long the storm can sustain it. A brief, weak tornado may last under a minute and span a few yards. A strong, long-lived one, like the tornado that crossed more than 20 miles of Effingham County, comes from a storm that holds its rotation steady for a long time, fed continuously by warm inflow and strong shear. The long-track tornado is not a different beast. It is the same process running longer and more efficiently. Knowing how a tornado is born explains why forecasters speak in odds rather than certainties. They can identify the storms capable of producing one. They can warn the areas at risk, but the final step, whether a given storm tightens its spin into a tornado at a given moment, sits partly beyond what can be predicted. That is why a warning means take cover now, not wait and see. The notice is built around what is known, with room left for what is not. That uncertainty is exactly why the words forecasters use, watch and warning, carry such weight, and why knowing the difference between them can decide what you do with the minutes you have. Those terms are worth getting straight. The difference between a watch and a warning is next. Two words decide how a person should respond to a coming storm, and they are easy to mix up. A watch and a warning sound similar and mean very different things. Getting them straight is one of the most useful things anyone in storm country can do, because the right word tells you exactly how much time you have and what to do with it. Begin with the widest layer, the one that comes first. Days or hours ahead, the Storm Prediction Center in Oklahoma issues an outlook. That is the broad heads-up described at the start of this report, the map with the risk levels drawn on it, from marginal at the low end up through slight, enhanced, moderate, and high. An outlook covers a large area and a whole day. It does not mean a storm is coming to your street. It means the region is at risk, and it is the signal to make a plan and stay aware. The moderate risk that went up a day before the worst outbreak was an outlook. The middle layer is the watch. A watch is issued when conditions are becoming favourable for severe storms or tornadoes over a particular area, usually for the next several hours. It is the difference between knowing a region is at risk and knowing the ingredients are now actually coming together. A tornado watch, like the one that covered nearly 5 million people across eastern Missouri and central Illinois, means tornadoes are possible in and near that area soon. The plain way to remember it is this. A watch means the conditions are right, so get ready. Know where your shelter is, keep away to get alerts, bring in anything that could blow away. A watch is the time to prepare while you still have time. The sharpest layer is the warning. A warning comes from the local National Weather Service office, in the moment, for a small and specific area, when a severe storm or tornado is actually happening or about to. It is based on what the radar shows or what a trained spotter reports seeing on the ground. A tornado warning means a tornado has been spotted or is strongly indicated by radar in your immediate area. The plain way to remember it is this. A warning means act now. A watch is the time to prepare. A warning is the time to take cover. That single distinction, prepare versus act now, is the whole point. People who confuse the two lose the advantage the system is trying to give them. Someone who treats a watch like a warning may take shelter too early and too long, and stop trusting the alerts. Someone who treats a warning like a watch may wait and watch the sky when they should already be in their safe place. The words are chosen carefully. Matching your response to the word is what keeps the warning useful. There is a simple way to keep the layers straight in order. The outlook is the forecast for the region, issued ahead of time. The watch is the heads up that the storms are now likely nearby, issued hours ahead. The warning is the alarm that the storm is here, issued minutes ahead. Wide and early, then narrower and closer, then small and immediate. Each layer hands off to the next as the threat sharpens and draws near. It is worth knowing how these reach you, because a warning does no good if you never hear it. They come through several channels at once. Local television and radio break in with them, weather radios sound an alarm, and most phones now receive emergency alerts automatically for tornado warnings in their area, a loud tone and a message that arrive whether or not an app is open. Keeping that phone alert turned on is one of the simplest safety steps a person can take, because it will wake you for a tornado warning in the middle of the night when you would otherwise sleep through it. That overnight point matters for this event. Forecasters noted that the storms could keep their strength well into the night, which is more dangerous than it sounds, because nighttime tornadoes catch people asleep and unaware. A phone alert or a weather radio that wakes you is, in those hours, a genuine lifesaver. Knowing the words is the first half of staying safe. The second half is knowing what to actually do when the warning comes. The guidance is short, standard and calm, and it is worth having clear before you ever need it. What to do when a warning reaches you is next. When a warning sounds for your area, the right actions are few, simple, and worth knowing before the moment arrives. None of this is dramatic. It is the standard official guidance, and it works. The aim of this chapter is to leave you with a short, clear plan, so that if one of these storms ever reaches you, you are not deciding what to do for the first time while the wind rises. Start with a tornado warning, the most urgent. The core rule is to put as many walls between yourself and the outside as you can, and to get low. In a house or sturdy building, go to the lowest floor. A basement is best. If there is no basement, move to a small interior room on the lowest floor, a bathroom, a closet, or an interior hallway, away from all windows. The goal is to be in the most protected space in the centre of the building. Once there, get down low and cover your head and neck with your arms. If you can put something over you, a mattress, a heavy blanket, cushions, do it. Because most tornado injuries come from flying and falling debris, not the wind itself. Stay away from windows entirely. Do not open them. There is an old idea that opening windows helps equalize pressure and protects the house. It does not. It wastes time you need for shelter and lets in wind and debris. Leave the windows alone and get to your safe place. Some places offer little protection, and it is worth knowing them in advance. A mobile or manufactured home is not safe in a tornado, even one that is tied down. The standard advice is to leave it before the storm arrives and go to a sturdy building or a designated shelter nearby. If you are caught driving, do not try to outrun a tornado in a vehicle, especially in traffic or on unfamiliar roads. If a sturdy building is close, go to it. The least bad options outdoors are limited, and the real answer is to avoid being caught out, which is what the watch is for. The watch is your window to get somewhere safe before the warning ever comes. For a severe thunderstorm warning, the threat is mainly damaging wind and large hail, and the response is similar but less extreme. Get inside a sturdy building and stay away from windows, because 80-mile-an-hour wind and baseball-sized hail both break glass. Do not go outside to watch the storm come in. As covered earlier, straight-line wind can do tornado-like damage, and people underrate it. Treat the warning seriously and stay indoors until it passes. For flooding, which these storms also brought, the rule is the shortest in all of weather safety. Turn around, do not drown, Never drive into water across a road. It is almost impossible to judge how deep or how fast the water is, and it takes surprisingly little to float or stall a vehicle. Most flood deaths happen in cars. If you come to a flooded road, turn around and find another way. After any of these storms passes, a few cautions matter. Assume every downed power line is live and dangerous, and stay well clear of it. Watch for the smell of gas near damaged buildings, and if you smell it, leave and report it. Be careful moving through any structure that took damage, because floors and walls may be weakened. And check on neighbours, especially older ones or anyone who might need help, because in a small town the first help often comes from the people next door. The through line of all of it is calm preparation. Know where your safe place is before the season starts. Keep your phone alerts on. Have a way to hear warnings at night. When a watch is issued, get ready. When a warning comes, act. None of these steps is hard, and together they are what turn a few minutes of notice into safety. This guidance matches what the National Weather Service and local emergency managers advise, and it holds for nearly every severe weather situation, not just this one. Having it clear in your mind is the single best thing you can carry out of this report. After the storms pass and people are safe, a different kind of work begins. Teams go out to measure what the tornadoes actually did, to confirm their strength and their paths. How that careful accounting happens is next. Once the storms move on and people are safe, a quieter and slower kind of work begins. Teams from the National Weather Service go out to the damaged areas to find out exactly what happened. They are called storm survey teams, and their job is to turn the chaos of a storm into confirmed facts. This is why, in the hours right after an outbreak, the early reports describe damage, but the final numbers come later. The need for this work was clear in this event. After the outbreak, the office near La Crosse, Wisconsin, planned to send a survey team to the area near Harpers Ferry, Iowa, where a large and dangerous tornado warning had gone out. The office in northern Illinois planned to send teams to survey damage from the multiple tornadoes observed there. The teams know it will take time to get confirmed numbers, and they say so. They work as fast as they can while still getting it right. Here is what a survey team actually does. They travel to where the damage is and study it on the ground. They look at what was hit and how badly. A snapped tree, a roof partly peeled, a house with its walls down, a well-built structure swept clean off its foundation, each tells a different story about how strong the wind was at that spot. The team maps where the damage starts and stops, which gives the length and width of the tornado's path. They photograph, measure, and document, building a careful record from the wreckage. From that evidence they assign a rating. Tornadoes are rated on a scale called the Enhanced Fujita scale, which runs from 0 at the weak end to 5 at the violent end. The rating is not guessed from how the tornado looked. It is worked out backward from the damage. The team matches what they see against a detailed list of damage indicators, structures and objects with known breaking points, and estimates the wind speed that would have been needed to cause it. A roof gone from a sturdy, well-anchored house implies a far stronger wind than a few downed tree limbs. The worst damage along the path sets the rating. This backward method is worth understanding because it explains why ratings take time and sometimes change. The wind inside a tornado is almost never measured directly. There is rarely an instrument in the right place at the right moment, and the wind would often destroy it. So the strength is inferred from the damage it left. That is a careful, evidence-based process, and it is also why an early rating can be revised as teams gather more information. A first estimate of a tornado's strength may rise or fall once the full path is surveyed. That is not error. It is the process working as designed, refining the answer as the evidence comes in. The path length matters as much as the strength. By mapping where damage begins and ends, the team confirms how far the tornado travelled. This is how a claim like the Effingham County tornado tracking more than 20 miles gets verified. Someone walks or drives the path, finds the damage from one end to the other, and measures it. The long-track tornadoes, the ones that cause the most concern, get the most careful mapping because their paths cross the most ground and the most lives. There is a human side to this work that is easy to overlook. The survey teams arrive in communities that have just been hit, while people are still clearing debris and absorbing the shock. The teams move through the damage with notebooks and cameras, doing the unglamorous work of measurement. What they produce, though, matters a great deal. Their ratings and path maps become the official record. That record informs how building codes are written, how warnings are improved, and how the country understands its own risk over time. Each survey is one more data point in a long, patient effort to learn from every storm. The result of all this work is the confirmed history of an outbreak, assembled piece by piece after the fact. The number of tornadoes, their strengths, their paths, the damage they caused, all of it is built from the ground up by people walking the wreckage. It is why this report holds to confirmed first-hand accounts in the immediate aftermath and lets the surveys fill in the rest. The truest version of the story is the one the evidence supports, and the surveys are how that evidence is gathered. With the past accounted for, attention turns to what comes next. The pattern that drove this long siege has not vanished, and forecasters are already watching the days ahead. What the forecast shows, and what remains uncertain, is the next piece. The pattern that drove this long siege has not finished, and forecasters are already watching the next several days. The honest picture is mixed. There is more severe weather in the near term, and there are early signs that the stuck pattern may finally be loosening its grip. Both deserve a clear and measured look, with the uncertain parts marked plainly. In the immediate term, the storms continue. The Storm Prediction Center has flagged scattered severe thunderstorms stretching from the central high plains into the middle Mississippi Valley and the lower Ohio Valley, mainly through the afternoon and into the night. The threats are the familiar ones: large to very large hail, damaging winds with some gusts above 75 miles an hour, and tornadoes are all possible. Forecasters note that some potential for strong tornadoes may develop across parts of Illinois and Indiana, the same weary region at the center of this report. So in the very short term, the answer is plain. The pattern is still active, and the same areas remain at risk. Looking a few days out, the forecast points toward a slow shift. Heavy rain and the threat of flash flooding remain a concern across the Central Plains and the Mississippi and Ohio valleys, as repeated rounds of storms move along a lingering frontal boundary. Flooding, the quiet threat that often follows these storm trains, stays in the picture even as the most violent tornado threat eases. The standard caution holds: do not drive into flooded roads. The more hopeful sign is in the larger pattern. Forecasters describe the flow aloft beginning to relax into something more typical of summer. A ridge of high pressure is forecast to build across the southwest, bringing heat there, while the long-wave trough that has anchored the cold pool over the north starts to behave more normally. By the following weekend, forecasters expect an organised low-pressure system and a cold front to move across the northwestern part of the country, which would herald cooler weather for much of the west. If that holds, it would mark the kind of pattern change that finally breaks a block. The spring and summer setup would give way to a more ordinary summer regime. Here the uncertainty has to be stated honestly, because the further out a forecast reaches, the softer it becomes. The medium-range outlook notes that computer models, ensembles and newer guidance broadly agree on a pattern change, but that real uncertainty remains in the exact timing and location of the systems involved. Forecasters can see the shape of the change coming. They cannot yet pin down precisely when it arrives, or exactly where the last rounds of severe weather will fall. That is a forecast, marked as a forecast, and it could shift. What this means in plain terms is a guarded kind of relief. The near term still carries real risk today and through the next day or two for the central part of the country, including the same Midwest corridor. The longer term offers the first genuine signal that the relentless pattern may be winding down towards something calmer. Neither part is certain enough to bank on completely. The storms in the next 48 hours are likely. The pattern break a week out is probable, but not locked in. For anyone in the affected regions, the practical advice does not change with the forecast. Keep your phone alerts on, know your safe place, treat a watch as the time to prepare and a warning as the time to act. The fact that the pattern may be easing is no reason to let down before the last storms pass. The most dangerous moment in a long siege is often the temptation to relax just as the final round arrives. The morning lull on the worst day was a reminder of exactly that. So the next wave is real but likely not endless. The same ingredients that drove the month are still in place in the short term, which keeps the threat alive for now. The signs of change in the longer term are encouraging, with the careful note that they are still signs, not certainties. Forecasters will sharpen the picture day by day, as they always do, narrowing the wide early outlook into the precise warnings that come when a storm is actually bearing down. With the immediate future laid out, it is worth stepping back one more time to see this month in the context of the whole season, and to weigh honestly what is settled about it and what is still being argued. That wider view is next. Step back from the single outbreak and from the single month, and a larger picture comes into view. This stretch of weather did not appear out of nowhere. It is part of a season, and the season fits into patterns that play out across the country every year. Seeing the wider view helps separate what is genuinely settled about all this from what is still honestly debated. Start with the settled part, the ordinary rhythm of severe weather in the United States. The country sits where three great air masses meet. Warm, moist air comes up from the Gulf of Mexico. Cold, dry air comes down from Canada. Hot, dry air comes off the deserts of the southwest. Where they collide with strong winds aloft to organize the clash, storms can rotate and turn violent. This is why the central United States sees more tornadoes than anywhere else on Earth. It is not bad luck. It is geography, and it is well understood. That clash moves with the calendar in a known way. Early in the year, the action sits along the Gulf Coast. Through spring, it shifts into the deep south and then the southern plains, reaching a peak there in May and early June. Then, as summer deepens, the focus drifts north, into the northern plains and the Midwest, and later toward the Dakotas and the upper Midwest. The mid-June outbreak at the center of this report falls right where the season's normal path was heading. The region was due for its turn in the rotation. What was unusual was not that the Midwest got storms in June. It was how strong and how relentless they were. That brings in the factors that may tip a given season toward more or less severe weather, and here the honest course is to hold them loosely. One is the state of the Pacific Ocean. In a pattern often called La Niña, the broad flow across North America tends to shift in ways that favour more severe weather across the plains and Midwest. That is a tendency that nudges the odds over a whole season. It is not a switch that decides any one month. Forecasters track it as one input among many. The harder question is the long-term trend, and it deserves a careful, even-handed treatment. A warmer atmosphere holds more water vapour, and more water vapour means more fuel available for storms. Researchers are studying how a changing climate may be shifting where, when, and how often severe weather happens in the United States. Some signals are becoming clearer over time. The season may be lengthening at its edges. The geography of the risk may be shifting. Other parts remain genuinely uncertain because tornadoes and severe winds are small, brief, and historically hard to count consistently, which makes long trends difficult to pin down with confidence. The fair statement is this: it would be wrong to declare that this one active month was caused by long-term climate change, because no single month can be pinned on it. It would be equally wrong to declare that the broader trends had nothing to do with it, because the ingredients this month were unusually rich, and richer fuel is consistent with what a warming atmosphere supplies. The careful position, the one the evidence supports, is that the season setup was anomalous, that several factors may be raising the odds of such setups, and that scientists are still working out how much weight each factor carries. Anyone claiming full certainty in either direction is reaching past what is known. What is not in doubt is the value of holding a steady, informed view rather than an alarmed one. An active season is striking, and it is also something the country has seen before and weathered. The record it is chasing was set nearly 2 decades ago. The systems that warn people, forecast the storms, and rebuild afterward worked through this month as designed. Knowing the rhythm of the season, understanding the ingredients, and respecting the genuine open questions is a far more useful stance than either panic or dismissal. The wider view, then, is one of a well-understood machine running unusually hot, for reasons that are partly clear and partly still being studied. The storms are explained, the season's path is known, the deeper drivers are a mix of settled science and active research. That is the honest shape of the bigger picture. With the season placed in context and the open questions named, only one thing remains: to return to the event itself, gather what is known and what is not, and say plainly what comes next. That final accounting is the last chapter. Return, at the end, to where this began. Something formed over the Midwest, and now there is a clear account of what it was. On the 17th of June, a powerful storm system swept across the region and set off one of the strongest outbreaks of the year. That much is settled, confirmed by measurements, by reports from the ground, and by the work of the people who track these storms for a living. Here is what is known: tornadoes touched down across at least 6 states. One of them crossed more than 20 miles of Effingham County, Illinois, among the most significant of the day. In Steinsville, Indiana, a tornado collapsed part of a building's roof, and crews worked to reach the people inside. Hail fell as large as baseballs, 3 inches across, in several Illinois counties. Straight-line winds reached near 80 miles an hour across a wide area, with a gust of 94 miles an hour clocked in Iowa during the morning's windstorm. More than 82,000 homes and businesses lost power. A single forecast office issued 58 warnings in one day. None of that is in question. What is also known is the cause of the storms themselves. A deep pool of cold air sat aloft, far enough south and deep enough to belong to spring rather than summer. Around it ran an unusually strong jet stream near 80 miles an hour, supplying the wind shear that made the storms rotate. Warm, moist air streamed up from the Gulf to fuel them. A stuck pattern overhead, a block in the flow, held the whole arrangement over the same region and kept aiming it at the same map day after day for the better part of a month. The storms were forecast before they formed. The mechanism is understood in detail. Here is what remains uncertain, stated plainly. No one can yet say with full confidence why this particular block set up when it did, why it favoured this region, and why it held as long as it did. Blocks form and break for reasons that sit at the edge of what forecasting can predict beyond a week or so. Larger factors may be tilting the odds, the state of the Pacific and the longer trend in the climate among them, but how much each one contributed to this single month is still being worked out. That is the honest answer to the title's question. The storms are explained. The deeper cause of their persistence is not fully settled, and the careful thing is to say so. The full toll is also still being counted. Survey teams are walking the damage paths, measuring how strong the tornadoes were and how far they travelled. Those numbers will firm up in the days ahead, and early ratings may be revised as the evidence comes in. The grid will be restored over hours and days. This report is held to confirmed accounts, and let the surveys fill in the rest, because the truest version of the story is the one the evidence supports. As for what comes next, the picture is mixed and worth watching. In the short term, the pattern is still active. More severe storms are likely across the central part of the country, including the same Midwest corridor, with hail, damaging wind, and a tornado threat. Heavy rain and the risk of flooding follow close behind. Further out, there are early signs that the stuck pattern may finally be relaxing into a more ordinary summer setup, though the timing and the details remain uncertain. The thing to watch is whether that pattern change arrives on schedule and breaks the long siege, or whether the block holds a while longer. For anyone in the affected regions, the steady advice carries through to the end. Keep your phone alerts on, know your safe place, treat a watch as the time to prepare and a warning as the time to act. Do not relax before the last storms pass. because the most dangerous moment in a long stretch is often the lull that feels like the end. That is where things stand. A strong, well-understood outbreak, born of an unusual and stubborn pattern, sitting inside one of the most active starts to June on record. The storms are known, the persistence is still being studied, the next rounds are on the way, and the longer-term break is probable but not certain. The watching continues as it always does, and the next report will follow the pattern wherever it goes,